All right, hello. My name is Sabrina. I am an academic graduate appointee for Lawrence Livermore National Lab in the States. I work for the Center for Applied Scientific Computing. And today I'll be presenting some work that we've done on a project called EGSTRA, or EGRAPHS-based structures for test suite reduction and abstraction. So to give some context for the problem that we were trying to address, suppose you're testing a tool that takes tree-structured input. This applies to tools that take in schema-based documents like XML, or tree-based data structures, or abstract syntax trees. For our specific problem, we were using abstract syntax trees that were generated by Clang from C programs, like the simple C program on the left, to get tree-structured output that looks something like the one on the right. And when testing this tool, we ran into a very common problem. The tool had no established test suite. This is usually the case. And the way that most developers address this problem is to build test suites from actual inputs that the tool is expected to handle. That could be done through regression testing or unit testing. However, as you likely know, this approach is very time and labor intensive. Additionally, the test suite is not guaranteed to cover all of the full range of input that the tool is expected to handle, and you may end up with a lot of redundant test cases, which can make the testing process a lot less efficient. It also, depending on your problem, it may be impossible to generate test cases based on the actual input for the tool due to the presence of an abundance of extraneous information or sensitive information. In terms of extraneous information, you may have a case where it's difficult to just run a processing script on your input and remove all the things that you don't need, but you still need to find a way to efficiently filter out parts of the input program that aren't relevant while retaining all the salient parts of the program for testing. And for our specific use case, if you've ever looked at an abstract syntax tree generated by Clang, it's very messy. There's a lot of unnecessary information in there, like IDs and information about the header files. And since we're trying to test on programs that literally already have millions of lines of code, it's really not helpful. So we had to find a way to filter that out while still maintaining the integrity of the input trees. Additionally, this is an issue that we at Lawrence Livermore run into a lot, but it can come up in other places where you have sensitive information in your input. Maybe that's due to regulatory constraints on your data, like maybe you're working with health information that's censored to protect a patient's privacy, or maybe your stakeholders are concerned about copyright or proprietary information. At Lawrence Livermore, we also have security concerns, so different members of a team may have different levels of access to essentially clearances about the data. And so you need to make sure that all members of the team can view the information about the input that you're processing. So this is sort of a different instance in which you need to ensure that the tool can handle this sensitive information in the program, but you need to find a way to abstract that out. So given the problem context, we began asking this question: without an established test suite, how can we develop a test suite that best demonstrates the correctness of a tool operating on tree-structured input? Of course, what is best is really going to depend on the context in which the tool is being used. For our tool, we are concerned about lessening the redundancy of the test suite to obtain a smaller and more efficient test suite, while still ensuring that we test the tool on the full range of the content that it's expected to handle. Of course, there are a number of ways to approach this problem. The perspective that we took was one that is analogous to the process of distillation, but we were using EGRAPHS instead of cold water. So we still hope to extract test cases from real tool input, as is done in the traditional case, but we hope to use EGRAPHS to filter out or abstract any unnecessary or sensitive information. And after filtering out and abstracting, we wanted to distill the structures of input programs into smaller test cases. And when I'm talking about program structure, I'm talking about programming patterns like an accumulator pattern, or control structures like for loops and conditionals. So we're really talking about like a syntactic analysis of the program, or syntactic perspective. I wouldn't necessarily call it an analysis. But to give more input, or to give more insight into how this workflow works, we can walk through it here. So As I said, we're starting with these large JSON inputs that were generated by Clang. We're then feeding those into a traditional EGRAPHS structure and leveraging the hash consing to identify any overlap in the program structure and content. From there, we wanted to abstract any sensitive or unnecessary information using what we call extended rewrites. These are rewrites that allow for term replacement and deletion. And once we moved to this eGraph that allows those features, we then apply these traditional equivalence relations to address any remaining redundancy in the input. And after that, we use the extraction functionality to extract these test cases that capture the structure and the content of the larger input while minimizing redundancy. So the bulk of our research focused on transitioning from this traditional eGraph to an eGraph that allows replacement and deletion. And there are a couple of key ways that you need to modify the implementation to allow this functionality. So first, you obviously need to modify the rewrite rules to allow you to delete and replace terms. So we introduce the notion of like destructive rewrite rules in our implementation. You also need to ensure that the hashcons data structure can handle the way that term removal propagates through the data structure. You don't want to lose any integrity in that data structure. And of course, we had to change the implementation of the union find to allow an efficient deletion. So to show this workflow in action, we implemented a Python-based domain-specific language for Turtle. If you're unfamiliar with Turtle, it does exactly what it's doing here. It's just used to draw and create graphics like this little fractal drawing program. And it also has a lot of repetitive commands. So as we see this drawing, we see a lot of ways that this program structure could be distilled into just a few commands where you're going forward, turning left, right, changing the angle. And the inputs to our DSL look like this little JSON file on the right. So we have commands to modify the turtle cursor, like teleport, set heading, and go forward. We also have binary operations, variables, and constants, so just very simple DSL. So the first rewrite rule that we are going to write for this little DSL is an extended rewrite rule, so just showing off this functionality. And the motivation for this extended rewrite is to discard any details that might obscure patterns in the structure of the input program. So this eGraph here, this represents the call to change the angle of the turtle cursor just by passing a binary operation to the function, so subtracting y from x. And this eGraph here, so slightly different than the way that, it's just a different like aesthetic, I guess, but we still have boxes, we still have terms representing this eGraph. So what does it look like when we supply this rewrite rule to our implementation? So this rewrite rule, what we're going to do here is we're going to remove distinct variable names and replace them with underscore, because for the purposes of testing our tool, it only matters that it can handle variables when they're passed to binary operations or variable assignment. And so it really doesn't matter if the name of that variable is foo or bar or x. This has come up in a number of presentations as well, sort of a context-dependent equivalence. But for our context, it is equivalent, so we're going to do this rewrite. And so what this is going to look like is we're going to supply a pattern match here. So we're going to match terms that have a type var and they have a keyword of name. This $n here is a meta variable. So we're just going to match any value that is associated with the keyword of name here. We could put constraints on this meta variable, and in fact, we did write a parser to do so. So you can say $n has type string. That would be fine. You can do finer constraints than that too. But just for the purposes of this demo, we're just going to match everything. And after you supply that pattern match, what you're going to do is you're also going to provide part of this rule that is going to tell you what you want to replace those terms with. So here, we still have type var, but the name's going to be rewritten to just be an underscore character. So in this eGraph, the terms in teal are the ones that are matched by the pattern that we provided here. So we're matching type var name x and type var name y. And that removal is going to propagate due to the sharing relationships and the hashcons. So we see that more than just those nodes that pattern matched are going to be identified for removal. And so because the parent term obviously contains type var name x and type var name y, that's going to get slated for removal and replacement. And because x and y's parents, all of their parents are going to be removed from the eGraph, those will also be removed. Note that var is actually not going to be removed, because even though its parents are deleted, it's going to be referenced by the term that is replacing it. And so when we're doing deletion and replacement on these eGraphs that are absolutely enormous, like the one that was shown in the second talk of the day, we don't want to do any unnecessary cleanup, just to improve the performance of this tool. After deletion and replacement, we get something that looks like this. The green text is nodes that have been added to this eGraph. So we see that the parent term doesn't have any references to the specific name of the variable. And of course, we have this new term that we specified should be added to the eGraph, type var name underscore, and of course the underscore. So essentially, we have rewritten this program to be turtle.angle, and then some variable minus another variable. So here, this is just a traditional equivalence rewrite. I'm sure we're all familiar with it. The syntax is a little messy, so I didn't put the rule up here. But this is just to show that you can still do the things you're accustomed to in this eGraph implementation. So if I just wanted to establish the equivalence of associative addition to mark this term on the left, the 1 plus, in parentheses, 2 plus 3, equivalent to the term on the right, 1 plus 2 plus 3, I can just apply a traditional equivalence rewrite to put them in the same equivalence class, with one node being promoted to the canonical node. So these are still allowed. You can still do these. And finally, we're going to do one final rewrite. So we're going to make all of the constants equivalent regardless of their value. Again, for the purposes of testing our tool, this is a valid rewrite because we just want to ensure that the tool can handle the way that constants behave in the program as arguments to functions and in binary operations, variable assignment. But of course, this rule may not be valid in a different context, so these are context-sensitive equivalence rules. So on the left, again, we have this pattern matching here. So we're matching terms that have type constant value $V. Just a meta variable, we're going to match any value that is associated with the keyword value, not constraining it. And then we're going to replace those terms with terms that look like just type constant. So just throwing out that key of value entirely. So starting with the eGraph on the left, again, the teal is the nodes that have been matched by that pattern matching rule. So we have type constant value 105 and type constant value 120 being matched. And of course, that's going to propagate through the eGraph, as denoted by the red arrows here. So because of those relationships, because of that sharing in the hash cons, those nodes are also going to be affected when this rewrite rule is applied. So after that's applied, we get this rule like the one on the right. So of course, we've added type constant to the eGraph. The parent term has also changed because it contained that subterm. So again, no reference to the values of the constant, just type constant. And of course, constant has not been removed from the eGraph. We've maintained the integrity of the rest of the eGraph independent of the rewrite. The last way that we had to modify the traditional eGraph implementation was by implementing the way that we, or by modifying the way that we implemented the union find data structure. So classical union find, typically it doesn't have any way to enumerate the members of a set, only test equivalence or identify a canonical set representative, which is a problem when you want to delete something specifically. So first we had to ensure that we were implementing a version of union find that allows us to identify peers in the same set for a pointer cleanup. But the problem was the performance was really, really bad. So in the baseline implementation, the performance was big O of n, where n is the size of the union find data structure. And we wanted to improve upon that, so we identified an algorithm that was proposed by Kaplan, Shafrir, and Tarjan in a paper from 2002. And this deletion algorithm, it just proposes a few adjustments. So first, it proposes cleaning up when half of the nodes are marked deleted, so not every single time. And of course, applying path compression. So here, in this very simple example, we don't clean up when we remove x. Only after we mark x and y for removal do we perform cleanup. And then path compression would mean that if z had any children, they would be directly connected to w rather than continuing to be chained. And this decreased the runtime to big O of n, where n is just equal to the set size. So of course, after all of these changes, we wanted to know how efficiently EGSTRA applied these rewrite rules to the input files in our DSL. So we gave it 100 files with about 110,000 lines of code total with that turtle DSL code. And we found that the runtime was about 3 seconds, which is pretty good. And that change in the deletion algorithm, it cut our runtime by over 99%. So to give an idea of what this means, we had another experiment that had several million lines of code, and it took about 2.5 hours to apply like 3 rewrite rules, which is very bad. And after this deletion change, it took 20 seconds, which is much better. In addition to performance, we also wanted to measure how the rewrite rules allowed us to compactify the eGraph and identify more similarities in the input program. And to measure this, we devised a sharing metric. There are, of course, other ways to measure the sharing in the eGraph. We just found this to be a helpful way of seeing how the eGraph changed over time, given that many of these eGraphs contain lots of nodes and lots of equivalence classes. And so if you can't look at it and see how the sharing has changed over time, then this metric is helpful. So the metric just corresponds to the average number of times that a unique term appears in the subtree of a root node in the hash cons. Each root node in the hash cons does stand for a different input file, unless you, for some reason, have identical input files in your input. I wouldn't recommend that. But here we plotted that sharing metric for every single root node in the hash cons. And at the start, we see that sharing was typically between 1.5 to 2.5 for all of those root nodes. After applying the rewrite that changed the name of the variables, we saw that sharing increased slightly to between 2 and 3. The plus, of course, so this was a traditional equivalence rewrite. We should not have seen any change, and luckily we did not, because that shouldn't be affecting the hash cons. That should only be affecting the union find data structure. So good sign, no change. In terms of the constants rewrite, we found that after we applied that rule to discard the specific values of the constants, we saw sharing increase pretty significantly for most of the root nodes. So we see sharing between 3 and 7 for these root nodes, with a few outliers that started with low sharing to begin with. But given that 99 out of 100 root nodes had increased sharing, we consider this to be a good result. That suggests that these rewrite rules are effective at exposing these underlying similarities in the input programs. So finally, we come to the extraction of test cases from the eGraph, which is what this project was intended to accomplish. So suppose we just want to extract all the terms that represent operations in the eGraph. We would do so by pattern matching terms with this simple pattern to find nodes that are rooted at a node of type op. So we're looking for subterms here too. And what we were asking was, do these rewrite rules actually lessen the redundancy of extracted test cases, and are they effective in highlighting key program structures? So before the rewrites were applied, all of the rewrites, we found that we matched about 4,700 terms, which is high. And after the rewrites, we found that we extracted about 143 terms, which is, of course, much lower. And what these extracted test cases looked like was what you see here. So these are actual results from our extraction. The V stands for variable, the C stands for constants. Obviously, these test cases, wouldn't compile if you fed it back in to test your tool, but you could populate these variable and constant values with whatever you would like. But we see that these test cases, we see that they are enumerating different combinations of different operations, which is exactly what we're hoping to test the tool on if we're applying this extraction pattern of type op. So we see that these rewrites have really allowed us to compactify the eGraph and identify the most salient parts of the program, as is highlighted by these test cases here. And of course, because the test cases are built from the input programs, they should be just as comprehensive as the input programs in actually testing the tool. So in future work, if you read our abstract, you should know that our engine is currently in C++. Not a good place to be when you are managing so many different data structures. Tough to work with, so it's a good thing that we're transitioning to a memory-safer language. We ended up choosing Swift just because Swift seems to have good interoperability with a lot of the code that we've already written, if you've seen the recent announcements from Apple about changes to Swift. Also, of course, increased memory safety, managing those different data structures, stricter type checking, and ML-style pattern matching have all been really helpful. In terms of actual features that we want to add to our implementation, we're interested in implementing a feature that we've called provenance tracking. This is similar to sort of the proof reconstruction idea that's in some implementations of the eGraph. So we want to recover the sequence of rules that has led to the existence of an extracted term. First, to actually verify that that term is valid in the context of the rewrite rules that you've applied. And second, there's this question when you have destructive rewrite rules is, when have I gone too far? When have I tossed out information that I actually need? Sometimes it's okay to lose information if you don't care about the information, but if you're losing information that you do care about, we can try to reconstruct the original term from the terms that we've produced to determine if it's a valid reconstruction based on the rules that you have given to the tool. Additionally, we want to implement some cost functions for extraction that are relevant to testing. So you may have different factors that impact what kind of test cases you want to look like. Maybe you want more complex test cases, simpler test cases, or test cases that feature different things. So we're hoping to have more fine-grained control of the actual tests that we're extracting. And of course, we're continuing to performance tune this tool for our intended use case, as I mentioned, which contains millions, if not billions, of lines of code. We're also interested in application to test suite deduplication, but even there, we're operating on millions to billions of test cases. So we need to make sure that this tool is highly performant. And since that deletion seems to be a bottleneck, we're interested in refining that deletion algorithm further to improve deletion in the union find implementation. All right, thank you for listening. Do we have time for questions?
All right, thank you so much for the great talk. We do have time for a few questions.
I had two quick questions. One was on slide 19. It was about what does the x-axis within each thing represent? Because I saw that variables and plus, they look a little different on the x-axis, even though they're the same.
Yeah, I believe the order of the way that they were plotted was a little different. I was curious about this too, but I think when I went through and manually reviewed the metrics here, they were identical. So the array is identical, but for some reason when I'm plotting them, I think the order is slightly off. I think this is more of a Python MATLAB issue than it is an issue with the data, but that's a good question.
Makes sense, thank you. And then the question about sort of going too far, could you compactify the data more by treating like addition and multiplication and negation, like turning them all into addition? Does that seem like something that would be useful, or would that be like way too far for?
Would it be useful? I think it would depend on your use case, but these rewrites currently are lawless. So you can do totally incomprehensible rewrites and say, for my purposes, plus is the same as division and subtraction. There's no limits on that. That's really, it's up to the user to decide. But I think a question that arises there is, should it be up to the user to decide? Should there be limits on the kinds of rewrites that you can apply? Or should there be guardrails or warnings? You know, this is going to result in a lossy equivalence rewrite when you're deconstructing. That's definitely a question that comes up. So you can perform that rewrite, but it's like, should you? Yeah, thank you.
Thank you.
I've got one question. One thing I noticed about some of the nodes is that their sort of compound type was a map. Looks like you're modeling JSON, and maps are typically sort of associative and commutative within their keys, right? And that's something that can be a challenge for other eGraph applications. So does your pattern matcher sort of handle that, or are the keys ordered, or
not ordered?
Was that a challenge to implement?
Yes, it was definitely a challenge. One of our concerns, since our team, I work on a team that's focused on verification, but of course we're collaborating with people who are not experts in PL, so we wanted to make the parser for pattern matching and this whole tool as accessible as possible. And so trying to make it easy for users to write their rewrite rules in a way that they don't have to be so careful with the way that they specify their rewrites, just in terms of syntax and whatnot, and the kind of strictness of the rules. They don't have to account for ordering, so that's automatically handled. And you can also, this is important to note. So for a rewrite rule like this, so a lot of these terms are very, very, very long. So what you can actually do is if you have a lot of keys and a lot of values, you can just provide an ellipsis and not have to make any specifications for the rest of that term. So I could do type var name $n, and the term could have 100 more keys, but I don't have to make any specifications about what those should look like. So.
Thanks so much. And let's thank our speaker.